Hello again to another Agacalera React. Today we'll be watching When a Billion Years Disappeared from PBS Ian's. And I started liking that channel more and more. And just starting with the view of Grand Canyon, so let's just get into it and just watch.
When geologist Clarence Dutton first saw the Grand Canyon in 1880, he was spellbound by its colorful walls. The Grand Canyon's walls are made up of rock layers, each representing a distinct period of Earth's history. And some of the lower rock beds deep down in the Grand Canyon looked kind of tilted. Dutton knew these layers were made up of very old sediments. Originally, they had been laid down as horizontal beds, mostly in rivers or shallow seas. Then the sediments hardened over time and geologic forces pushed some of the layers upward at an angle. As time passed, the tops of these tilted layers were sheared off by erosion, and later, new layers of sediment, which stayed more or less horizontal, were deposited right on top of them. And he knew every step of this process took time, because you generally don't get horizontal layers on top of tilted ones unless there's an age difference between them. In his examinations of the Grand Canyon, Dutton got a first-hand look at what geologists call an unconformity. Basically, that's a gap in the geological record. It shows that sedimentation didn't happen continuously, and that there's an age difference between sets of rock layers, and sometimes that age gap can be millions of years or more. In 1882, Dutton named this particular break the Great Unconformity. At first, nobody realized just how great it was. Today we know from radiometric dating that the rocks directly on top of the Great Unconformity were laid down during the Cambrian period, about 500 million years ago. But in some places, the rocks below this Great Unconformity are about 1.2 billion years older. That's a big gap. I mean, the Earth itself is only about 4.5 billion years old. So at this spot in the Grand Canyon, 25% of the planet's entire history is gone. Those layers just aren't there anymore. And the Grand Canyon isn't the only place where this happens. You can see the gap from Siberia to Antarctica and plenty of spots in between. Scientists are still trying to figure out what caused the Great Unconformity, but they have some ideas. This missing chapter in Earth's history might be linked to a fracturing supercontinent, out-of-control glaciers, and maybe, just maybe, the diversification of life itself. Sedimentary rock layers are formed by a process called deposition, when eroded geological materials, like sand, are laid down by wind, water, or even ice. They accumulate to build up layers of sediment that later turn into rock. And when you've got a layer of rock that's distinct from everything above and below it, that's called a stratum. Pile up a bunch of strata on top of each other, with each level representing one span of time, and together they'll create a rock sequence. And an unconformity is a boundary dividing two strata with an age difference between them. An unconformity might mean that no new material was deposited at this place for a long time, interrupting the rock sequence. But this isn't always the case. Usually, unconformities are made when an entire layer gets eroded away somehow. And it turns out that the Grand Canyon's picturesque walls are full of unconformities. For example, there's a 150 million year gap between two strata of limestone, a layer from the early Carboniferous period and another one from the Cambrian period. But that's nothing compared to the Great Unconformity. It begins under the Tapete Sandstone, a stratum laid down by the ancient tides of a shallow sea about 508 to 501 million years ago during the Cambrian. Below this, you'll find a stretch of 1.75 billion year old metamorphic rock called the Vishnu Schist, along with tilted rock layers ranging between 1.25 billion and 740 million years old, known as the Grand Canyon Supergroup. And figuring out what happened in that gap is the key to explaining the existence of the Great Unconformity. Right now, we're living in the Phanerozoic Eon, which began 541 million years ago at the dawn of the Cambrian period. But before the Phanerozoic, there was the Proterozoic, a much longer eon that kicked off some 2.5 billion years ago. And yeah, that's billion with a B. The Proterozoic saw the rise and fall of 3 supercontinents, and the last one is known as Rodinia. Scientists think that it formed between 1.3 billion and 900 million years ago, and when it was fully assembled, Rodinia contained just about all the known continents that were around at the time. But supercontinents don't last forever. Rodinia started breaking apart around 750 million years ago, well before the Cambrian started. And its breakup might have been linked to something else that happened late in the Proterozoic. It would have been another major event, and a pretty cool one, literally. Since the 1930s, scientists have been finding evidence that glaciers were common at the equator late in the Proterozoic. Places like Western North America and Southern Australia were tropical or subtropical back in those days. And if you look at deposits from the late Proterozoic, you'll find a haphazard mixture of sand, mud, gravels, and boulders. Those deposits are called tillites, and they're the material that gets left behind by glaciers. In places that were at low latitudes during the late Proterozoic, geologists often find these tillites sandwiched between limestone beds that probably developed in warm tropical waters. This finding, along with paleomagnetic data and other clues, gave rise to the snowball Earth hypothesis, which I've talked about before. According to this idea, glaciers once covered all or most of the world's surface, from the poles all the way down to the equator. And this may have happened more than once in the late Proterozoic. So there could have been multiple snowball Earth episodes, with the first starting around 716 million years ago and the last one ending just 635 million years ago. And these cold periods might be related to the Great Unconformity, but how depends on who you ask. Either the formation of the Great Unconformity was part of what caused snowball Earth, or snowball Earth was what formed the Great Unconformity. One study published in 2018 made the case that the Great Unconformity helped set up the start of snowball Earth. It looked at North America's Ozark Plateau, where 500-million-year-old Cambrian sandstone sits on top of granite that's 1.4 billion years old. Here, as in the Grand Canyon, the Great Unconformity is plain to see. To date the Great Unconformity, they used uranium isotopes and helium trapped in zircon crystals. From those crystals, they concluded that the area was tectonically uplifted and eroded from about 850 to 680 million years ago, and this coincides with the breakup of Rodinia. Tectonic uplift on a big scale may be a side effect of fragmenting supercontinents. In this case, the study's authors think several kilometers of rock were lifted up only to get whittled down by erosion. Since the Ozarks were really far inland back then, the scientists think there was a continental-wide, maybe even worldwide outbreak of large-scale erosion. If this really was a global phenomenon, it may be what created the Great Unconformity, eroding away rock layers that now appear as gaps in the geological record. And there's more. The authors think the erosion of all that Proterozoic bedrock affected the climate by capturing large quantities of carbon in the Earth and its oceans, keeping it out of the atmosphere. That's because rainwater often pulls carbon from the atmosphere during the weathering process. Since rainwater is weakly acidic, it dissolves rock and releases ions. These ions can get washed into the ocean where they form calcium carbonate, which is eventually buried and traps the carbon in the rock. And carbon's a key component of greenhouse gases, so if a lot of carbon didn't end up in the atmosphere, that might have promoted global cooling, along with other factors like volcanic events and a dimmer sun. And as the world grew colder, glaciers could have gone unchecked. In other words, welcome to Snowball Earth. So, according to this timeline of events, Rodinia's breakup resulted in lots and lots of erosion. And not only did that erosion create the Great Unconformity, but it also impacted the climate, helping to set the stage for Snowball Earth. But not everyone agrees. A different study published in 2019 argues the opposite, that Snowball Earth's glaciers created the Great Unconformity by grinding up the surface of our planet. The glaciers would have eroded away a lot of the outer continental crust, dumping it into the oceans. This massive increase of eroded material would have also increased the amount of crust being driven down into the Earth's mantle, where some of it was recycled into fresh magma and sent back towards the surface. And the evidence of this comes, again, from isotopes trapped in zircon crystals. But this time, they're isotopes of the element hafnium. Some hafnium isotopes are more likely to form at the surface than down in the mantle, and that signature is preserved. This can show where the isotopes came from. And remember, zircons are also used in radiometric dating. So by looking at the ratios of different hafnium isotopes in these zircons and dating the zircons themselves, the researchers figured that the crust erosion and recycling probably happened after Snowball Earth started. And this is because they found a lot of surface hafnium trapped in the zircons, and the zircons formed after Snowball Earth got underway. So if that's true, the erosion and all the crust recycling that would have gone with it could not have set up Snowball Earth. Instead, it could have been glaciers that stripped away over 1 billion years worth of rock layers, creating the Great Unconformity. Or at least that's the hypothesis. Hopefully, future research will tell us which came first, the snowball or the unconformity. But either way, the loss of so much material could have been important for life on Earth. Complex life really diversified during the Ediacaran period, which closed out the Proterozoic, and then life exploded during the Cambrian. Scientists have wondered if this might be related to Snowball Earth and the Great Unconformity. Some researchers have suggested that when all that crust was destroyed, it fundamentally changed the ocean's chemistry. The weathering process might have transported a lot of geologic material from land to the sea. As a result, scientists think our oceans were filled with calcium, potassium, iron, phosphorus, and other vital elements. This could have revolutionized life on our planet by giving it the chemical building blocks it needed to really get going. One hypothesis even suggests that these new ingredients help to encourage biomineralization, the process by which living things create minerals for their shells and skeletons. So maybe when Clarence Dutton first saw the Great Unconformity way down in the Grand Canyon, he was actually looking at the calling card of a phenomenon that made his own existence possible. I must give big shout-outs to all these researchers who consulted on this episode. Your input was greatly appreciated. Also, grand high fives to this month's eontologists: Patrick Seifert, Jake Hart, John Davison-Ing, Sean Dennis, and Steve. Become an Eonite by pledging your support at patreon.com/eons. And thank you for joining me in the Constantine Haase studio. If you like what we do here, subscribe at youtube.com/eons.
Okay. That was quite cool, and this is the second time I hear about the snowball era. I have to look into that. And yeah, geology, science in general is interesting. Do you think? 1 billion is missing, and they can't really come to consensus of what was the reason for it. Well, I'm not going to find out either. This is why I'm watching stuff, so I can learn from what people researched. Okay, thank you very much for watching, and I'll see you tomorrow. Bye!